Ever wondered how a machine could make a complex decision? Not with some crazy, complicated black box algorithm, but with a simple series of yes or no questions, just like you would? Well, that's exactly what we're breaking down today, the decision tree, one of the most intuitive and powerful tools in machine learning. We're going to go from the basic idea and the math behind it, all the way to building one from scratch in Python. So let's dive right in.
So how does this actually work? Honestly, the best way to think about it is like a game of 20 questions, right? You start with a really broad question, and every single answer you get helps you narrow down the possibilities until, boom, you land on the right one. A decision tree does the exact same thing with data, and that simple idea is the key to everything.
So here's our game plan. First, we'll cover the intuition and the math. Then, we'll get our hands dirty with the classic Titanic dataset using Python. After that, we'll actually train the model, see how well it did, and finally, we'll talk about the really important difference between a simple tree and a more complex one. All right, section 1. Before we write a single line of code, we really need to get inside the mind of a decision tree. It's all about figuring out how to turn total chaos into clarity by asking the best possible questions in the right order. You see, at its core, a decision tree is just a flowchart. It starts with this big, messy pile of data, in our case, every passenger on the Titanic. And its entire goal is to ask questions that split them into smaller and smaller, more pure groups. And by pure, I mean a group where almost everyone shares the same outcome. You want to end up with a bucket of people who almost all survived, or another bucket where almost everyone didn't. That's the goal. And this brings us to a really important idea from mathematics: entropy. Just think of entropy as a number that measures messiness or randomness. If a group has high entropy, it's a total toss-up, completely chaotic. If it has low entropy, it's orderly and predictable. The entire job of the decision tree is to ask questions that crush that entropy, bringing it as close to zero as possible.
And this is the perfect way to picture it. If you have a group of 10 passengers and all 10 of them survived, that's perfect purity. There's zero messiness, zero uncertainty, so its entropy is zero. But if you have a group of 5 who survived and 5 who died, well, that's a 50-50 split. That is maximum chaos, maximum uncertainty. And we give that an entropy value of 1.
Okay, so here's the million-dollar question. How does the tree decide which question to ask first? Are you male or female? What class ticket did you have? It figures it out using something called information gain. For every single possible question it could ask, it calculates how much that question will reduce the overall entropy. Then it just greedily picks the one question that provides the biggest drop, the highest information gain. That's it. That's the secret sauce. All right, enough theory. Let's see how this plays out in the real world. We're jumping from the concepts into the code. We're going to use Python and the famous Titanic dataset to see if we can predict who survived. So here's a quick peek at our data. Every row is one passenger. The columns like sex, P-class, which is their ticket class, and whether they were alone are our features. Think of these as the clues. And that survived column, that's our target. That's the answer we want our model to learn how to predict. Now we've hit a super critical step, and this is something that trips up so many people when they're starting out. Machine learning models, especially the ones in scikit-learn, don't understand words like male or female. They only speak in numbers, so we have to convert that text into numbers, a process we call encoding. And here's the result after we do that. In Python, this is actually pretty easy. You can do it with a simple one-liner, something like dfSex equals dfSex.map male 0, female 1. And just like that, male becomes 0 and female becomes 1. After that, we split our data into 2 piles, a training set for the model to learn from, and a testing set that we keep hidden away to see how well it performs on data it's never seen before. Okay, section 3. This is where the magic really starts. We're taking our clean, all-numbers dataset, and we're about to hand it over to the algorithm to let it find the hidden patterns that predict who lives and who dies. Believe it or not, training the model really only takes a few lines of code, but every single word here matters. First, you import the model from scikit-learn. Then, you create it. That's this line, dtModel equals decision tree classifier ... Now, let's break that down. By setting criterion equals entropy, we're telling it, hey, use that information gain and entropy math we just talked about to find your splits. Then, max depth equals 3 is our safety net. We're telling the tree, don't ask more than 3 levels of questions. This stops it from getting way too complicated. And finally, dtModel.fit, xtrain, ytrain. The .fit command is the magic button. It tells the model, okay, look at all these passengers and their outcomes and start learning the rules. And we're on to section 4. So, the model is trained, but is it any good? We have to check. It's time to test it on that data we held back. And then, this is the best part, we're going to look right inside its brain. This report gives us the cold, hard facts. Let's just focus on that survived row. Precision of 0.83 means that when our model predicted someone survived, it was right 83% of the time. Not bad. And a recall of 1.00? That's amazing. That means our model successfully found every single person in the test group who actually survived. It didn't miss a single one. For such a simple model, these results are fantastic. And now for my absolute favorite part about decision trees. You know, a lot of modern algorithms are what we call black boxes. You put data in, you get an answer out, but you have no idea what happened inside. Decision trees are the total opposite. They're a white box. Their superpower is that we can pop the hood and see exactly, step by step, why it's making the decisions it is. And here it is. This is literally the logic our model learned. Right at the very top, at the root, the model figured out that the best first question to ask, the one with the most information gain, was about the passenger's sex. If sex is less than or equal to 0.5, which for us means it's a male, you follow the path to the left. If not, you go right. And see the colors? The darker the shade of orange or blue, the more pure that group is, which means the model is more and more confident about its prediction. Now remember, we deliberately kept our tree simple by setting max depth to 3. And that was a very intentional choice, which leads us to our final and maybe one of the most important concepts in all of machine learning, the bias-variance trade-off. Okay, so a shallow tree like ours is simple and fast. We say it has high bias, which is a fancy way of saying it makes some pretty strong, simple assumptions and might miss some of the finer details. But it has low variance, which means it's less likely to get thrown off by random noise in the training data. This is great for avoiding a huge problem called overfitting. On the flip side, a really deep tree has low bias but high variance. It can learn incredibly complex patterns, but it's also in massive danger of just memorizing the training data, including all its quirks and noise. When that happens, it performs terribly on new data it's never seen. Finding that perfect balance is the name of the game.
So, how do we fight back against these overgrown, overfitted trees? Well, one of the most common ways is a technique called pruning, and it's exactly what it sounds like. After we let the tree grow, we can go back and strategically snip off the branches that don't really add much predictive power. This simplifies the model and makes it much better at making predictions on new data.
So you can think of a single decision tree as one detective, carefully following a trail of evidence to reach a conclusion. But what if, instead of relying on just one detective, you could assemble a whole squad of them, let them all investigate independently, and then take their majority vote? Well, that's the idea that leads us to our next topic, random forests. But it all starts right here with understanding a single, elegant decision.
Like and subscribe for Simplify Tech, explaining one concept at a time, simplifying the technology and AI.